Hi everyone, so in the previous video we talked about capacitors in series and parallel. We learned that for series Q is the same, whereas the voltage you need to sum them up, whereas for parallel the voltage is the one that is the same and the charge you need to sum them up. Then using these two equations, we have arrived at an equation that relates between the individual capacitance and equivalent capacitance. So this equation is for series and this equation is for parallel. So moving on from that, we are going to study what is the amount of energy stored in each of these capacitors when it reaches a certain level of charge, when it reaches a certain level of potential difference. Okay, so we learn how does the charge and knowing the charge stored, knowing the potential difference of a capacitor, how do we determine the energy stored in the capacitor? Okay, so the title for this part of the video is the energy stored in the capacitor. Okay, it's a very short part in your syllabus actually, because we don't really need to know how does all the equation comes into place. You just mainly need to know how to use it only. So I'm going to just write down what is needed in your syllabus. Then after that, you can take a pause of your video and just move on to the questions. But as you can see here, I've prepared quite an elaborate plan over here because I'm going to give you an overview of how does this equation comes into place. It's not really in the syllabus, but I just feel like maybe I can try to share it with you. But if those information are not needed, feel free to stop it once I introduce you what is relevant to our syllabus. Okay, so the energy stored in the capacitor, the symbol of energy stored is U. It's because the energy stored is actually electric potential energy as well. So the unit for energy, as usual, from a semester 1 and semester 2, the unit is joule. So you can use it as J. Okay, so the energy stored, the symbol is U. But we are going to talk about just the equation. Okay, so the equation that we can use to determine how much energy is stored in the charged capacitor, it can be described as this equation: U is equals to half QV. Okay, so that means by if we know the amount of charge stored in a capacitor and we know the potential difference between the two capacitor plates, if you just take half multiplied by the charge stored and the potential difference, you are able to get the energy stored in this particular capacitor. Okay, of course, if there are situations where you are connecting capacitor in series or parallel, let's say there are multiple capacitors, right? You need to keep track. Let's say I'm interested in the energy stored in the second capacitor. Then that means this is U2, it's not U1, it's not U3, okay? The second capacitor. So I need to multiply half with the charge stored in the second capacitor, Q2, with the potential difference across the second capacitor, V2. So I have to keep it consistent. If I'm asking for U3, then it's half Q3, V3. If it's U1, then half Q1, V1. You have to make sure you know which charge are you substituting in, whether it's referring to the same capacitor where you are finding the energy. Okay, moving on from this equation, you also know the definition for capacitance. Capacitance is the ratio of Q over V, right? So you know that capacitance C is equal to Q over V. So if you adjust a bit the equation, where you can say Q is equals to CV, you can rearrange the equation that way, so that once you put in you replace the Q here with CV, it becomes CV multiplied by V. So U will be equals to half CV squared. Okay, running on a similar idea, you can replace the V instead. You know that based on the same equation, V is equals to Q over C. Okay, V is equal to Q over C. So if you replace the V over here with Q over C, you can see that the Q becomes square. So U will be equals to Q square. Then you have 2C. Okay, so the C here becomes squared because how should I say it? If you put in the Q over C inside, the Q becomes squared, but the C, there's only one of it, so it's over 2C like this. Okay, of course, if you want to continue to complete the triangle, you know that this Q over here, if you replace it with CV, you replace the Q over here with CV, then you get this equation: U is equal to half CV squared. Okay, so these are the three equations. any equation can be used. There's no particular situation where only one equation can use, one equation cannot be used. All of these are equivalent. They can be used at any time depending on what information you have. Let's say you have Q, you have V, then this is suitable for you. You have C, you have V, then this is suitable for you. You have Q, you have C, then this is suitable for you. So look at the situation, look at what information you have, then you can just pick the right equation. Okay, so that's it for our syllabus actually. So from now on, I'm going to talk about how does all this equation comes into place. I'm going to try to explain in a way in which I imagine the situation, and it can get a bit fuzzy and it can get a bit murky because I'm not really polished. I haven't really polished my explanation yet. I tried a few times actually recording this video. It all was a bit jumbled up, but I'll just try to explain it in the way that I understand. If you can understand, that's good. If you cannot understand, feel free to talk to me more to discuss the idea. Okay, so to illustrate the idea of how much energy is being stored in a capacitor, I'm going to show you how a capacitor is being charged and discuss about the energy change that happen to those charged that when they move from one plate to another. Okay, so this is a charging process. So the charging process means by you initially have an uncharged capacitor. So an uncharged capacitor means by it is initially neutral on both plates. So I'll draw it to be neutral on both plates. Okay, so not just the positive charge, of course, it is neutralized because there's the same amount of negative charge in each plate as well. Okay, so right now I can tell you confidently that there's no charge stored in this plate initially, so the charge stored is equals to 0. At the same time, because there's no charge stored in the capacitor, you should expect that there is no potential difference across the capacitor as well. So you can see that at this stage, you can see that V capacitor, the voltage across the capacitor is equals to 0 at this stage. Okay, but when I started my charging, okay, let's say this is T is equals to 0. When I started my charging, what happened is the battery here will act as a charge pump, right? So it will move charges, positive charges from low electric potential region to high electric potential region. It converts its chemical energy to provide to the charge so that they can move from low electric potential region, which is this negative terminal here, to a high electric potential region, which is this positive terminal here. So since the positive charge are moving from negative to positive terminal, it's moving in an upward direction, passing through the battery. So you know that positive charge will have to be drawn out from this lower plate and you have to be deposited on the upper plate. Okay, so I'm going to focus on only the first charge that is going to move right now. Let's say this is the charge that will move first. I'm going to study the motion of this charge from the lower plate up until it reached the upper plate. Okay, so this is the charge that moved the earliest during a charging process. This is the charge that moves the earliest. Okay, so there are two kinds of energy thing that I'm going to study regarding this particular charge that moved the earliest. The first thing I'm going to study is what is the energy change when it passes through the battery. When the positive charge passes through the battery, what is the energy change to the positive charge? Okay, then the second thing I'm going to study is when the charge moves from one plate to another. When it moves, when it arrives maybe. Okay, when it arrives at the upper plate. Of the capacitor. Okay, I'm going to study this particular two situation and I'm going to study how much energy change happens to the charge. Okay, when I say energy change, it means the gain in electric potential energy, or the loss of electric potential energy. So in order to study this, the equation I'm going to use to study the energy change is delta U. So delta U comes from first chapter, when we know that delta U is equal to Q delta V. Okay, so this is the equation that I'll be using in order to discuss what's going to happen here. Okay, so if we are only focusing on the region focusing on the part of the journey where the charge passes through the battery, that means by we are only focusing, let's say when it passes through the battery, that means by it can be from here, which is initial, until here, where this is the final, because we are only focusing on the change in energy when this charge here is going to pass through the battery. Okay, so we are going to apply this formula to study the situation. So delta U is equals to Q delta V. Okay, I'm focusing on the charge that is moving the earliest, therefore I'm going to change the symbol Q to become the Q first, or Q earliest. Okay, then I have my delta V, which is from initial to final over here. So final here is actually the positive terminal. So I'm going to write this as the positive terminal. And then minus, the initial was here, right? This is the negative terminal. So I'm going to write V plus minus V minus. And actually, if you go through this thing, if you take V plus minus V minus, that means by you're taking the positive plate or the positive terminal electric potential minus the negative terminal electric potential, which will result in the electric potential difference, and the potential difference is actually just the potential difference of the battery. So to make it simple, I'm going to say this is just Q earliest multiplied by the voltage of the battery. Okay, I think that makes sense. Okay, it's a bit confusing over here. This thing represents potential difference. This thing also represents potential difference, but this thing is electric potential. This thing is electric potential. So I'm going to use back chapter one's way of writing. So I'm going to write this as the potential difference of the battery. This is electric potential, positive terminal, minus electric potential, negative terminal. So you find the difference, right? That's why this is potential difference of the battery. I'm just using back the old way of writing because I'm talking a lot about electric potential here. Okay. So continuing on this journey, you know that the charging will continue to happen. So besides having the initial 6 positive charges over here, maybe you have another 2 or 3 more charges already moved in already. Okay, so down there might be 3 less positive charge compared to earlier. Okay, so the charging is happening midway. So we know that here there's an amount of charge, which I'm going to call it as Q. Here there's also a certain amount of charge, which I'm going to call it as negative Q. Okay, so this is the amount of charge being stored right now. So I'm also going to say that this is called, the VC right now is moderate. Okay, is equals to, let's just call it as V moderate. Okay, there's some amount of charge being stored. So it's a very small Q over here, it's a very small over here. It's a very small negative Q over here. And because the charge stored is still very little, the potential difference across the 2 plates is also moderately small. So right now the voltage across the capacitor is just moderate. Okay, so right now I'm going to investigate the charge that moves a bit later. Okay, so 3 charge has already moved upwards. Now I'm focusing on what's happening to the 4th charge. Maybe I shouldn't draw this charge because this charge technically has moved already, right? Okay, let me shift. Let me look at another charge. Okay, let's say let's say I'm focusing on this charge, okay? This charge is now moving. So you go in, go here, go here, go here, and you enter here, right? Okay, so again, I'm going to study the another charge, but this time this charge is a charge that is moving later during the charging process. Okay, so this is the charge that moves later. Okay, if you again focus on the journey when it passes through the battery, you still move and you pass through the battery. So you can still see that it's the same initial and it's the same final. And during the charging process, you are definitely not swapping the battery. It's still the same battery throughout the process. So you can confidently say that the potential difference, which is V final minus V initial, will still be the V battery because it's still the same battery over here. Okay, so you can say delta U is again once again equals to Q delta V, but this one is no longer Q earliest, this one is Q later, and this one is still V plus minus V minus, so therefore you still get the Q, same Q late, but this one is later Q, and it's still the same delta V battery. Okay, again, I'm not focusing on the whole journey of the charge from the lower plate to the outer plate. I'm just talking about when it passes through the battery, how much energy gain does it receive. Okay, you know that the battery supplies energy, right? So this is the gain in energy that the charge have when it passes through the battery. The gain in energy when it passes through the battery. Okay, so continuing from that, I'm going to focus on the last charge that is going to move up right now. Okay, so initially we have something like this already. Then you add on with some charges that's already moved up. Down there, it's still the same 6 of them. But down there, there's only one charge left. Okay, the last charge that will be moving. Okay, so right now let's talk about this last charge that is going to move across this plate, move across the circuit so that it can be deposited on the upper plate. Okay, so the charge that moves last. Okay, again, if you go look at the situation when it passed through the battery, it's still the same battery, even though it's still the last charge right now. So you still expect the same initial, you still expect the same final. So if you look through the situation, before you look through the situation, this is fully charged already, right? It's the last charge, right? It's the last charge that is going to go to the upper plate. So it's fully charged already. We'll probably say that this is a positive Q, or sometimes Q naught to represent that it's full already, whereas this thing down here will be negative Q naught to represent it's fully charged just as it's in the negative. Okay, so at this moment you can say that the potential difference over here it's at its maximum already, and you know that since it's connected to the battery already, it's connected to the battery, so that's why it should be equal to the voltage of the power supply. Okay, this one refers back to section 1. We talk about when it is connected to a battery, the voltage across the capacitor is actually locked by the battery over here. So if the battery is 1.5 volt, then the voltage across the capacitor at the end of the charging process will also be 1.5 volt. So at the end of the charging process, we should expect the voltage here has reached its maximum. That's why V naught C, and it's equal to the voltage of the battery, which is the maximum right now lah. Okay, so going through the same idea, find again the change in energy. Again, you see that it's still the same battery, so nothing has changed. Even though it's the last charge that is moving, you still get the same quantity. You still pass through the same quantity of potential difference. So this is Q last. This will be V plus minus V minus. So that's why this will still be Q last, and your potential difference will be delta V of the battery. Nothing has changed across the whole sequence over here. Everything is the same. Okay, so why do I spend some time to talk about everything that is the same? Because I'm going to plot the graph later. This is the amount of charge, amount of voltage that it passed through. Okay, this is voltage V or delta V in chapter 1. This is just Q. Okay, right now I want you to think about the whole x-axis over here as little charge. So I can imagine that this is the charge that moved the earliest. This is the charge that moved a bit later. And then this is a charge that moved last. Okay, the correct concept is to talk about dq, which is very small amount of charge. Okay, so actually you can slice the you can slice the x-axis here to be dq, 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 dq. So it's like this is the first charge that moved, the second charge that moved, the third charge that moved, up until the last charge that can move. I'm simplifying a situation that I'm drawing just 3 charges. Okay, but I can think of it as the first small amount of charge, the second small amount of charge, the third small amount of charge, the fourth small amount of charge, up until the last amount of charge. This is the idea of the that I'm illustrating here. Okay, so the first earliest charge went through a potential difference of how much? The first earliest charge went through a potential difference of delta V battery, right? So we should expect that over here, you should experience delta V battery over here, where this value is equals to V battery. Okay, but the charge that moves later will also went through the same potential difference, which is the V battery, right? So it will still be here. Okay, whereas the last charge that moved through the battery will also went through the same amount of potential difference. So you should expect that it should have the same height as well. So if we draw a line that connects all the delta V, we see that it's a straight line. Okay, so continuing from that, you also learned that delta U, the amount of change of energy, is Q delta V, right? You see that this is Q, this is delta V, right? So if you multiply them, you get the change in energy. So what does it mean? If you go find the area under the graph over here, this area under the graph will give you the energy. Okay, but this one is not really energy stored in the capacitor. This is energy supplied by the battery, because we are focusing on the battery, right? This is energy supplied by the battery. And you can see the energy supplied by the battery is actually just taking U is equals to Q, which is this thing. It's a rectangle, right? It's a rectangle, so Q times V. This is energy supplied by the battery. Okay, so I've spend some time to explain to you things that happens all the same way from initial until final. But right now I'm going to move to part B over here. When things move to part B, you get a bit more interesting right now. Okay, so right now we are studying the change in electric potential energy when the charge moves from here, the lower plate, up until you reach the final plate. Okay, so right now the initial and final position is a bit different. This is our initial position when it just come up from the lower plate, whereas this position here will be the final position. Okay. okay, when it arrives at the upper plate. Okay, so we know that delta U is equal to Q delta V, and we are focusing on the earliest charge that moved right now. Okay, so if you want to do this, this should be V final minus V initial, right? So we write this as V final, or we can see V of the upper plate minus V of the lower plate. Okay, but if you notice over here, V upper and V lower right now, because there's no charge stored across the capacitor, there's no potential difference at all across the capacitor, right? So the VC right now is equal to 0. That means by V high, V upper and V lower, there's no potential difference across them. Why is there no potential difference? Because there's no charge stored. So this value over here, V upper minus V lower, because there's no charge stored, the electric potential are the same for both plates. So if you minus it, the difference will be equal to 0, right? So because it's equal to 0, you know that this one is just Q earliest multiplied by 0. So technically, there's no gain in energy at all when the charge moves from initial lower plate to the upper plate for the first charge. Okay, so if you think about it, what's happening over here is when the charge is coming out here, nothing happened, nothing happened, nothing happened, nothing happened, nothing happened. But when it passes through a battery, it gains an amount of energy which can be determined by using this equation. If you sub in, let's say 1 volt battery, 1 coulomb charge, then that means by when the 1 coulomb charge passes through this 1 volt battery, you get a 1 joule of energy. You get a gain of 1 joule energy when it passes through the battery. But based on the green calculation over here, you see that when the charge arrives from initial to final, you see that there's no change in energy. So that means by even though you gain an amount of energy over here at the battery, when you arrive at the upper plate, you are supposed to not have any change of energy compared to initial. Means that if you go up already, you somehow have to go back down so that there's no change in energy. It's just like let's do it like this. Okay, I'm telling you that this is the initial place where you start your journey. This is the end point where you end your journey. I'm telling you right now that there is no changes to the number of food that you have on your hand. Let's say you have 2 Snickers bar on your hand. You have 2 Snickers bar on your hand. I'm telling you that there's no change into the amount of Snicker bars that you had when you come back here. So if you happen to gain 5 Snickers bars from this battery, let's say you receive 5 Snickers bars from this battery, and you know that there's no change at the end, you still arrive at 2. That means by what you receive here, you have to throw it out immediately. What you receive, the amount of energy that you receive from battery, you have to give it out somewhere before you come to the upper plate. Because you know that there's no change in the amount of energy, there's no change to energy when you arrive here. Okay, initially, let's say it's 5 joule, when you reach here, it's 5 joule. Okay, so if you happen to receive 5 joule over here, you become 10 joule, right? But you tell me that I'm going to reach here with 5 joule. That means by that 5 joule that I gain, I need to lose it back to somewhere. Okay, so where am I losing the energy to? Well, actually, if you enter section 3 later, you know that this kind of charging circuit, there must be a resistor over here. Okay, and let's don't put it here. It makes things a bit difficult to understand. Okay, let's put the resistor somewhere over here. Okay, so how does this resistor fit into the picture? It's because let's say you have 0 joule in the beginning. Let's say 0 joule in the beginning. When you pass through the battery, you gain 5 joule of energy, right? But you need to come back to the upper plate with 0 joule energy because initial final is the same 0, no change, no difference. So that amount of 5 joule energy that you gain over here, you have to lose it to this resistor over here so that you can come back here with 0 joule of energy, same as initial. So that total 5 joule energy will be wasted to be given to this resistor and it will be dissipated as heat. That's why initially the amount of energy supplied by the battery will all be directed to the resistor to be released as heat. No amount of energy is stored initially at the start. Okay, 0 energy initial, 0 energy final. So if you gain 5 joule in the middle, you have to throw that 5 joule away to the resistor so that you can come back here with 0 joule at the end. Okay, that's what happened to the earliest charge. Okay, now the next charge that is moving right now it will experience a net potential difference over here. Right now there's charge stored in the capacitor already, right? So there's charge stored in the capacitor, means that there's some voltage over here already. There's some potential difference over here. So initially, let's say you have 0 joule over here, you reach here, because there's a potential difference, you can probably have 2 joule. Okay, if it's 0 over here, when you reach here, probably you can have 2 joule. So that means by if you gain 5 joule from here, if you go pass through the battery, you gain 5 joule, you might probably need to throw, no need to throw all 5 joule, you only need to throw 3 joule, so that you still have keep 2 joule to bring it here. So right now the amount of energy that you throw away is less. The amount of energy that you throw to the resistor become less as the charging progresses. Okay. So continuing, can say that for this green one, delta U is equal to Q delta V, but this one is Q later right now. Q later also need to go through the same V final minus V initial. So this is V upper minus V lower. Okay, but right now V upper and V lower does not equal to 0 anymore. They're different. There's some amount of charge stored, so there's a potential difference across them. So if there's a potential difference across them, there's a moderate amount of potential difference. So I will say that this is Q later multiplied by delta V, which is moderate. Less than battery, definitely. Less than the battery, but moderate. So let's say if this thing is positive 2, then this thing is positive 5, then what does it mean is from here to here, there's a gain of 2 joule of energy for every coulomb. Okay, there's a gain of 2 joule when you move from here to here. Okay, but you know that you gain 5 joule over here, as calculated over here. You gain 5 joule, that means by to come back to the upper plate, you have to throw 3 joule away so that you can come back with 2 joule. So when you throw the 3 joule away, you throw it at the resistor. So that means by initially the resistor will dissipate a lot of heat, but as the charging goes on, the resistor will dissipate less and less heat, because the amount of energy that is being directed to the resistor will become less, as more and more energy will be directed to be stored in the capacitor. Okay, and at last, when you move to the last charge that is moving, the last charge that is moving over here, it will pass through the battery. You still gain the 5 joule energy, let's say, but because the voltage across the capacitor is similar like a battery, it's like, let's say this is a 5 volt battery, then here also will be a 5 volt capacitor. So 5 volt capacitor means by if I start with 0, I can come back here with 5. Okay, a gain of 5. Okay, so if the battery supply me with 5 joule energy, I can just take that whole 5 joule energy and bring it into the capacitor. That means by at the end of the journey, at the end, near the end of charging, the resistor will receive near nothing. No energy will be dissipated as heat through the resistor. Resistor receive very gradually decreasing to 0 kind of energy. At the last charge that is moving over here will practically give no energy to the resistor at all. The whole energy that is supplied by the battery will all be carried into the capacitor. Okay, why is it so? It's because if you go through the calculation over here, delta U is equal to Q delta V. You see that the last charge over here, Q last, okay, is V upper minus V lower as usual. But right now, V upper minus V lower, because it's the last charge already, the potential difference over here is the same as the potential difference of the battery. Okay, so the last charge over here will experience the same amount of change. Okay, can you see here the same amount of change as it passes through the battery? So how much energy that you gain when you pass through the battery, that how much of energy gain will be passed to the capacitor, because it's the same. How much you gain from the battery is how much you stored in the capacitor. Okay, so no energy is being given to the resistor at all. So that's what happened for the last charge. Okay, so to slightly summarize it a little bit, initially the first charge, it moved through, it gains energy from the battery, but all of the energy will be given to the resistor. None will enter the capacitor at all, because none will enter capacitor at all as you move through the capacitor. Delta U is equal to 0. But as you slowly charge the capacitor up, there will be energy being directed to the capacitor. So the amount of energy directed to the resistor will gradually decrease, but the amount of energy directed to the capacitor to be stored will be gradually increasing. Until the end of charging, all of the energy be directed to the capacitor, where none of the energy be directed to the resistor. Okay, so that means by the energy supplied by the battery, right, not all of them are stored in the capacitor. Some of it will be dissipated as heat through the resistor. Okay, so if you want to show it in a graph form, right, again, I will show you, this is Q, this is V, sorry. If I want to show it in a graph form, this is the potential difference V. Okay, again, it's delta V actually in chapter 1. Okay, this is the charge. Right now, again, I'm going to talk about the earliest charge that is moving, the charge that moves later, and the charge that moved last. Okay, of course, if you see that initially, it went through a potential difference of 0. So you can label 0 over here. Later, it went through a potential difference that is moderate. So let's just put V moderate over here. Then at the end, it passed through an electric potential that is equivalent to the battery. So we can write it as something like this. Okay, so if you draw a line, you see that this forms a straight line, where this will be V battery. Okay, so again, if you go find the area under the graph over here, utilizing what we learned from this equation, Q multiplied by V, you will get the change in energy. So Q multiplied by V is just finding the area over here. This time, you will find energy as well, but this is not the energy supplied by the battery. This is energy stored in the capacitor. Okay, I think just by your naked eye, you can see that this is actually a triangle. So if you attempt to find the area for this triangle, you know that's just half multiplied by the width, which is Q, multiplied by the height, which is V. And this is how you manage to get the equation for energy stored in capacitor. And as you can see, the energy stored in the capacitor is actually half of the energy supplied by the battery. Okay, so how do you arrive at so this is how I understand why there's a half in front. It's because half of it is actually being dissipated through the resistor. This part over here is given to the resistor. It's just released as heat. You only get to keep half of it in the battery. Half of it is released as heat. Okay, if you really want to go through this whole process, this whole finding area thing using integration, okay, you can use integration as well. Okay, if you want to use integration, how do I do this? Okay, let's write like this. If I want to try to use this, find area under a QV graph. Okay, I believe most of you here are quite well versed with integration. So the energy stored will be the area under the graph. So it will be going from integration from this first charge over here will be 0, whereas the final charge over here will be maximum Q, right? Okay, so it will be from 0 to Q. Okay, this line over here, okay, this line over here, how I'm going to describe it, is the line of Y, right? Okay, let's write it somewhere. Okay, we learned before that if you want to find the area under the graph, Y is equals to area is equals to Y dx, right? So right now our Y is the voltage, so we're going to put voltage inside here, whereas the X over here is our Q, so we're going to put dq over here. Okay, so this is the equation that helps us to determine the area under the graph. So you go from 0 to Q for your charge, and this line over here is the Y, right? Okay, Y is our V, whereas the dx over here is dq. Okay, V here, we know that it will be changing with time, so let's change it to something else. We know that Q is equal to CV, right? So if we know that Q is equal to CV, we know that actually V is equals to Q over C, right? Why do I want to change it this way? It's because now I know that Q is constant. I can bring it out. Q is not constant. C is constant. The capacitance is constant. You are not changing a capacitor at all. You're not changing an area. You're not changing a distance. You're not changing the dielectric. You're not adding or removing dielectric. It's the same capacitor. So the C will not change. C is constant. You can bring it out. So if you bring out the C in front, right now you just need to integrate this Q over here, which will allows you to know that this is actually Q squared over 2, right? So Q squared over 2, then you have Q, you have 0. So if you work through the integral over here, you take this substitute minus this substitute, you get the final answer where, oops, sorry, what's happening? This is just Q squared over 2C. Okay, so if you want to solve it by integration, you get U is equals to Q squared over 2C. If you want to solve it by looking at it as a triangle, this is just U equals to half QV. And of course, if you use the definition of Q is equal to CV, you can switch them around as what I've explained earlier. Okay, so I hope I managed to give you a little bit of picture why this equation comes into place. But the main idea is to know that initially most of the energy enter the capacitor. Most of the energy is dissipated as heat through the resistor. None of the energy actually enters the capacitor initially. But as you continue to charge it, you have some potential difference across the capacitor already, right? So when you have some potential difference across capacitor, more and more energy will be directed to the capacitor and less energy will be directed to the resistor. So the resistor will gradually dissipate less and less heat, and the capacitor will gradually store more and more energy. And at the end of the journey, the last charge will basically give all of its energy to the capacitor, leaving none for the resistor. Okay, so that's why you can see that it is gradually storing more and more energy, whereas this is gradually reducing the amount of energy that is being dissipated as heat in the resistor, and it forms an exactly half relationship over here. Okay, so that's it for energy stored in a capacitor. It's a bit long-winded, but as I see, it's not really in your syllabus. If you don't understand it, it's fine. Okay, let me just add on something. This, when you finish charge, right, the time you take to finish charge something is infinity. Okay, it will be explained in the next section. Okay, but if you don't really understand the whole explanation over here, never mind. Okay, you can if you really want to know, you can discuss with me. Okay, you can see me just contact me to discuss with me. Okay, but for your exam purposes, knowing this will be sufficient already, so don't worry too much about it. So that's it for this video. Thank you very much.